Hi, my name is Judah, and I'm a lead engineer on the MongoDB replication team. Today, I'll be talking about tunable consistency in MongoDB. This is Sam. Sam is a software engineer. Sam likes biking. One day, Sam tries unicycling. Sam loves unicycling. Sam wants to share unicycling with New York. So like many New Yorkers, Sam starts a company. You need to share. One way, one wheel. You need to share is like a bike sharing app, but singular. When choosing which database to use for you need to share, Sam turns to MongoDB. Sam wants to make sure that you need to share is always available. People will stop renting unicycles if they can't check them out. Even worse, what happens if you have a unicycle and can't check it back in? Sam uses MongoDB replica sets to guarantee high availability. Reading the documentation, Sam sees that operations take read concerns to control consistency. MongoDB offers many read concerns for different use cases, and Sam isn't sure which to choose. Sam wants all of the data and you need to share to be consistent. But obviously, there must be some reason to use these other read concerns. On top of the read concerns, Sam sees that MongoDB supports a wide range of write concerns. Sam sees that write concerns can cause waiting, and they don't want you need to share to be slow. Sam also reads that every operation can have a different read or write concern. Does that mean they should choose a different one for every operation? Or is it fine to use the same for everything? Sam doesn't know what to do and is worried that you need to share isn't going to work well without choosing the best read and write concerns for each part of the app. In Sam's story, you may find insight about your own business. MongoDB tunable consistency is incredibly powerful. I want to help you understand how to make your applications work exactly as you want them to, even when disaster strikes. Tunable consistency can seem opaque, even for the most experienced users. This story is going to make it simple. Sam has 3 pieces of functionality that are going to illustrate the trade-offs implicit in read and write concerns. We'll start by helping Sam with the Unicycle Checkin process. Then, we'll look at a warning you need to share will display when the rack you want is popular and may empty quickly. Finally, we'll implement a feed showing which of your friends are actively unicycling nearby. Let's dive into the code Sam writes for checking in unicycles when a user is done riding. Check-in is quite simple. All we have to do is push a given unicycle's ID onto an array in the document for the given rack. Let's walk through what happens when Sam puts this to the test. We start with a rack with one unicycle on it, unicycle 1. All of the replicas in the set have unicycle 1 in the rack's cycles array, and an entry for that write at time 1 in the app log. Zooming in on the primary, we see that at time 1, there is an app log entry for setting the cycles array to include unicycle 1. Sam now arrives at the rack with a unicycle they previously checked out, unicycle 2. Sam checks in unicycle 2, and the app sends a $push update as part of the check-in function to the primary. This pushes unicycle 2 onto the rack's cycles array. This also writes an app log entry with time 2 into the app log for the push operation. Zooming into the primary again, we see that now the data files have been updated, and there is a second app log entry at time 2 for the second update. After the write is durable to disk on the primary returns success to the app. The app notifies Sam that the unicycle was racked, indicating that the check-in was successful and that they can leave. Sam now walks away, confident that their unicycle has been checked in. Oh no! Lightning strikes the primary server, and the primary crashes and goes offline. Once one of the secondaries notices that it can no longer see the primary, it will run an election and step up to become primary itself. Now Alex comes to the rack with their own checked out unicycle, Unicycle 3. Alex checks in Unicycle 3 to the rack. The app sends a $push update to the new primary. This pushes Unicycle 3 onto the rack's cycles array and writes an op log entry at time 3 for the update. After writing the update to disk, the primary returns success to the app, notifying Alex it's safe to walk away. The remaining secondary eventually replicates the op log entry at time 3. This pushes Unicycle 3 onto the rack's cycles array in its own data. The crashed node will eventually be brought back online, and when it does, it's inconsistent with the other nodes in the set. After the entry at time 1, its op log contains an entry at time 2 for Unicycle 2, while the other two nodes have an entry at time 3 for Unicycle 3. The restarted secondary will attempt to replicate from the primary. And seeing it's inconsistent, it will have to roll back. The inconsistent secondary will roll back the write at time 2. This also will remove Unicycle 2 from the rack's cycles array. Now that the rollback is complete, the restarted secondary just appears to be a lagged secondary and will begin replicating like normal. It will replicate entry 3 from the primary and update its own cycles array accordingly. But now the database only thinks that Unicycles 1 and 3 have been checked in. The database, and you need to share as a result, will think that Unicycle 2 never got returned and has been stolen. Sam is on the hook for the missing unicycle. The problem here was that the data was inconsistent. But the inconsistency began with the update for Sam's unicycle, Unicycle 2, not being durable. Sam looks at the docs for what they can use to ensure durability. MongoDB's way of configuring the durability of writes is write concern. Write concern specifies how many nodes need to have replicated a write for that write to be acknowledged as successful. So Sam realizes that this update needs a write concern. But what write concern should it have? Sam didn't specify a write concern, so to start, they need to see what write concern they were getting by default. The default write concern is W1. This means that, by default, writes don't get replicated before returning to the client. This is exactly what we saw in our example. The $push updates returned to Sam and Alex as soon as the primary had processed them, and the writes were replicated later on. Looking at the docs, Sam sees that W-majority offers much stronger durability guarantees. W-majority waits for writes to be replicated to a majority of nodes in a replica set before acknowledging success to the client. This guarantees that if a majority of nodes are healthy, acknowledged writes won't roll back. Specifying W-majority, let's see what happens. We start back at the beginning, with Unicycle 1 racked and replicated. Sam arrives to check in Unicycle 2. Sam puts Unicycle 2 on the rack, which executes an update with $push on the primary. This time, rather than return success to Sam, the primary waits until the update pushing Unicycle 2 onto the cycles array has been replicated to a majority of nodes. This prevents the inconsistency we saw before. A secondary replicates the update, and only then does the primary acknowledge success to the client. Sam is able to walk away from the rack with the confidence that Unicycle 2 has durably been checked in. This ensures that the replicas will eventually converge consistently on a state where Unicycle 2 is checked in. So this time going through the example, after the lightning strikes the primary goes down, but one of the secondaries already has the right for Unicycle 2's check-in. Among the healthy nodes, the secondary with right 2 is the most up-to-date. So it is guaranteed to win the election for primary. The other secondary eventually replicates Unicycle 2's check-in. And when the down node returns, all 3 nodes are consistent, and there is no need for a rollback. So right concern majority fixes the bug. It's important to acknowledge that majority writes are slower than W1 writes. They have to wait for secondaries to replicate writes, instead of being able to respond successfully to the client immediately. In this case, that's fine. It's okay if we're checking in a unicycle to take some extra milliseconds, and users will likely not even notice. We wanted to see, in practice, how many writes are using each write concern. Here's how people use MongoDB Atlas, MongoDB's managed database service. We see that 16% of writes use W majority, and almost 80% of writes don't specify a write concern at all. They rely on the default W1 behavior. If those writes shouldn't roll back, that might mean those applications have a bug, or have extra logic to make up for the lost W1 writes. In those cases, W majority could simplify applications. At MongoDB, we think most applications should use write concern majority. Many large enterprises use write concerns to simplify their applications and make them more robust. But we will see that write concern majority isn't always the right choice. Let's move to the second function Sam wants to implement. Those of you who've used City Bike or other bike-sharing apps might have had this experience. You see 1 or 2 bikes are left on a rack, so you go to that rack a couple blocks away. By the time you get there, there are no bikes left. Many people saw the same rack and raced with you to get the last couple of bikes. To address this problem, Sam wants to add a warning whenever many people have viewed a rack and may be racing with you. To implement this warning, Sam increments a views counter every time a user views a given rack. After the last example, Sam wants to be explicit about which write concern they use. Last time, Sam wanted W majority. It gave consistent data and made sure that no writes were lost on rollbacks. The problem is that majority writes are more expensive than W1 writes. If every time a user looks at a rack, the app needs to do a majority write, it'll be sluggish. Sam will lose most of their customers to bike, scooter, or rival unicycle sharing services. We wanted to know how slow majority writes really are, so we did 2 experiments. We deployed 3 node replica sets with different geographical distributions. We then compared the latency of W1 and W majority writes. In the first experiment, we placed all 3 nodes in the same region, but different availability zones. We see that all writes are quite fast, that even at such low latency, W1 writes are twice as fast as majority writes. In our second experiment, we tested nodes split across multiple regions. Here, it's clear we pay a large latency cost for majority writes. But we do get the benefit of not losing any of those writes. For the rack interest warning, the risk of losing writes isn't very high. Users will never see the count, and it's just creating a warning that's a nice to have. We still want the warnings to be somewhat accurate, or else what's the point? We wanted to see how often W1 writes are lost in practice. In order to lose a W1 write, replica set must have a failover. So we started by seeing how frequently replica sets have a failover. we looked at 17,000 replica set deployments managed by MongoDB over the course of 1 week. We see here that in any given week, 60% of all replica sets won't have a single election, and 96% will only have one election. This hints at a pretty low but real risk of W1 write loss. To estimate how many W1 writes we could expect to lose, we did a simulation. We found that users can expect some, but not many W1 writes to be lost. Researchers find that the Weibull distribution is a reliable model for time between server failures. So we used that in our simulation. The latency shown here is between replica set members in our simulation. 100 milliseconds is approximately New York to Munich. 200 milliseconds is approximately New York to Tokyo. In even the highest latency configurations, over 99% of W1 writes were durable. This is clearly good enough for the rack interest warning, and likely good enough for many use cases. Seeing this data, the trade-off is clear, and W1 is the best write concern for this update. We don't want it to be slow, and we don't care if we lose some increments when a server fails. Finally, let's help SAM with their friend feed. We want to post whenever a user checks out a unicycle so their friends can see and possibly come join them to ride together. So, as part of the checkout function, we will insert into the posts collection specifying who is checking out which unicycle at which rack. Again, Sam asks which write concern to use for this insert. Sam thinks about the trade-offs here. This insert is going to happen on every unicycle checkout. So if we use W majority, we will need to pay the cost of replicating this write to a majority of nodes on every checkout. If we use W1 though, a post can roll back. Users might really enjoy the friend feed, and if a post rolls back, they might find the app buggy. They may be unable to connect with their friends who are writing and lose a lot of the value they originally found in the app. In this case, Sam is happy to pay the latency cost to ensure the friend feed doesn't lose any posts, and opts for write concern majority. The getFeed function, on the other hand, is a simple aggregation. It matches on the provided username and then looks up all posts from the user's friends. Remember that posts is a collection of documents with user, cycle, and rack fields. Unicycle also has a users collection, which has one document for each user. The name field contains the user's username, and the friends field contains an array of usernames of their friends. This then outputs an array of relevant posts in the feed field of the response document. Let's try out this pair of functions. We start with Alex going to check out a unicycle. When Alex checks out the unicycle, Adrian and Taylor, Alex's friends, have already checked out their own unicycles. Zooming in, we see the data files contain 2 posts, and the op log contains 2 op log entries, one for each insert into the posts collection. For clarity, we will omit the op log entry at time 1 for the remainder of the diagrams. When Alex checks out the unicycle, Unicycle sends an insert command to the primary. A new document is inserted in the posts collection for the checkout, and an op log entry for the insert is written on the primary. Since the checkout function does the insert with write concern majority, the insert waits for replication before returning success. Meanwhile, Sam is looking at the Unicycle app to see who is unicycling right now. Sam looks at the friend feed and sees that they have 2 friends writing, but they're pretty far away. Sam keeps checking for a minute to see if anyone else starts unicycling. Sam notices that Alex has started writing, and they're right nearby in Soho. Sam gets their own unicycle, and they head over to Alex. When we last left off with Alex, they were waiting for replication and checking out their unicycle. Hundreds of miles from Alex, a tornado hits the primary node of the set. The primary goes down. The client gets a network error, but it can retry as soon as a new primary is elected. By default, drivers will retry writes when they receive network errors. So in this case, Unicycle won't even notice the retry. A new primary gets elected, and the driver retries against the new primary. But unfortunately, this insert also gets a network error, this time due to a network outage. At this point, Unicycle gives up and gives Alex an error saying it can't release the unicycle. Alex leaves the unicycle, giving up for the day. Sam now arrives at Alex's rack and sees that Alex doesn't have a unicycle. Sam is disappointed because they rented this unicycle thinking they'd have a buddy, and Alex won't get to ride with their friends. This data consistency problem is really a problem of isolation. The getFeed function is reading data that wasn't durable and could roll back. Sam looks in the docs for how to configure a read's isolation. MongoDB's way of configuring read isolation is read concern. Read concern specifies which writes a given read is allowed to see and what data it's allowed to return to the client. This generally means that the server will read from a specific point in time in the past or wait to be able to read at a specific point in time in the future. But what read concern should Sam use? Again, let's start by looking at the last example. The last example didn't specify a read concern, so it was getting the default. The default read concern is local. This means that the read will return the most recent data written to the node, regardless of if it was majority committed. This is exactly what we saw in the example. getFeed returned a post that was not yet majority committed, and thus could roll back. So which read concern prevents reading data that will roll back? Since we're talking about isolation, the ANSI SQL isolation levels may be more familiar to some. MongoDB's read concern local allows reads to see data that can be rolled back. MongoDB only views writes as committed once they've been replicated to a majority of nodes in a set. So read concern local is MongoDB's equivalent of read uncommitted isolation. But in this case, we want read committed isolation. We want the read to only see writes that will not roll back, writes that are majority committed. MongoDB's equivalent of read committed isolation is read concern majority. So this sounds right to Sam. With read concern majority, a post won't roll back once someone's feed reads and shows it. This should fix the bug we saw before. Let's see what happens now that we use read concern majority. We'll start halfway through the last example when Unicycle is waiting for replication of the new post insert. The insert of post 3 has been written to the primary, but is still waiting to replicate to one of the secondaries. Like before, Sam is looking at the Unicycle app to see who is unicycling right now. This time, Sam doesn't see Alex writing their unicycle, and won't until Alex's post majority commits. If there's a tornado that takes out the primary of the set, Alex's post will never show up, and Sam will never check out a unicycle alone. So using read concern majority does fix the bug. But what happens if the majority write actually commits? Let's test if that works correctly. Back with Alex, the insert of post 3 has been written to the primary, but is still waiting to replicate to one of the secondaries. One of the secondaries replicates the third oplog entry, and now the primary can acknowledge the majority writes to the client. This will notify Alex that they are free to take their unicycle. I know that I'm accustomed to buggy applications, and so whenever I post something, I look back to make sure it got posted. Alex is no different. When Alex looks at their feed for who's unicycling, getFeed runs its aggregation to see all of the posts. This time, though, the read goes to a secondary. Unityshare wants to serve these reads as fast as possible, so sends the reads to the closest node rather than always to the primary. When the read arrives at the secondary, this is the state of the node. The data files contain only the first two writes, and the op log has an entry for each of those writes. And so, the read will return that Taylor and Adrian are unicycling. But Alex is confused and concerned. Where is the post saying that Alex is also unicycling? Will any of Alex's friends see that they're unicycling and come join? So read concern majority fixed the original bug, but now we have a second bug. Alex did an insert, but then a read immediately after didn't see that insert. Alex needs causal consistency here. The data seen by the read should have been caused by the insert. That causal relationship, though, was broken in this example. Luckily, MongoDB makes it easy to ensure causal relationships are maintained. All Sam needs to do is ensure that both the checkout and getFeed functions accept a session and pass it to all of their reads and writes that need to be causally related. Causal consistency is specified at a session level because you need at least two operations to make or break causal consistency. The session here explicitly enables causal consistency on all operations on the session. Causal consistency is on by default for sessions though, so just using a session should be sufficient. To see that this fixes the previous bug, let's look back at our example starting from the insert, with one of the secondaries having replicated that insert. The primary will reply with success, but this time it also includes its cluster time, which is the highest oplog time it's seen. Since causal consistency is enabled, the read is accompanied by an after cluster time, specifying the timestamps that the node needs to replicate before responding to the read. The secondary waits to process the read until it replicates the most recent writes that could be causally related. In this case, that means the secondary will wait to process the read until it has replicated the oplog entry at time 3. The secondary will eventually replicate the oplog entry for the third post at time 3 and apply it to its data. At this point, all causal events have been committed, and the read can unblock and actually do its read. Zooming into the secondary serving the read, we see that this time, the node includes all of the writes and all of the data. This time, the read returns that Taylor, Adrian, and Alex are all unicycling. We finally see the result we wanted. From Atlas, we can also see how often read concerns are used in practice. We see that almost no operations specify a read concern. Like with write concern, developers are likely leaving great power on the table that could fix bugs or simplify applications. But not you. You now know about read concern majority and causal consistency and can easily prevent data inconsistencies in your own apps. With your help, Unityshare is now live. And now, with Unityshare live and running smoothly, Sam never needs to ride alone. Consider which read concern to use for each of your reads, and which write concern to use for each of your writes to get the best performance possible. Use the default by choice, not because you haven't considered what other options are available. The default read and write concerns won't always provide the best behavior for your use case. Tunable consistency in MongoDB gives you great power, and with great power comes awesome apps and features. If you're interested in learning more, read our documentation or Tunable Consistency in MongoDB, a paper published by members of the Replication team at the Very Large Databases Conference in 2019, which was the inspiration for this talk. Thank you. It's been a nice ride.